In 2005, a group of European researchers from leading academic and industrial organizations discussed the future of computer systems design in the context of the HiPIAC network of excellence. There was a consensus that within a time frame of 10 years, the currently used techniques and methods for computing systems design would no longer suffice. A common vision was developed, and the idea of the Sarc, in short, Scalable Architecture Project, was born. A great computer scientist, designer, and visionary, Stamatis Vassiliadis, was one of the leading contributors. After spending many years at IBM in the United States and being responsible for the development of many of its mainframes, he returned to Europe and joined Delft University of Technology. He always strongly believed in the potential of the European research and development community, and Sarc was the vehicle on which to prove this. What we needed was an industrial revolution of computer system architecture, where we considered the design of computer systems as a holistic approach, where the hardware and the software components would be co-developed in a coordinated action driven by the application requirements. The motivation for Sarc was based on the following observations and predictions. 1. The technological developments.
Behind of me, we have the Mare Nostrum supercomputers. The supercomputers are instrument tools that help us to produce better science. Even the current supercomputers are very fast. We are trying to build supercomputers in 10 years from now that would be 1,000 times faster. The main constraint for producing this supercomputer is the power. In order to reduce the power, we need to use heterogeneous processor, accelerator based on FPGA or GPUs. This is the solution, and the problem is that we complicate the way we will program this supercomputer.
2. The computer design.
It may sound strange, but actually the software cannot keep up with the current developments in hardware computing systems. The reason being, for instance, look at the tools like the compilers that we use to program at a high level such computing systems, that the designers, the compiler designers, cannot keep up with the recent developments in single processor or homogeneous architecture that we are currently using in the market. So moving towards scalable heterogeneous architectures will only worsen the problem. The solution that we are finding to this problem is that we need to balance appropriately the responsibilities assigned to the application developer, the compiler itself, and the runtime system, all this through well-thought programming models.
3. Convergence of embedded, commodity, and supercomputers.
Supercomputers, commodity systems, and embedded systems are converging. There are embedded systems today that outperform supercomputers of several generations ago. And there are supercomputers that are built from processors originally designed to be embedded. Heterogeneous processors and accelerators are becoming the norm rather than the exception. And for that, we're going to have to develop a unified system design methodology if we're going to allow industry to maintain its current efficiency.
For the first time, the industry was struggling to increase the speed of processors at the same rate as the number of transistors on a chip was scaled. Innovative architectures were needed, which were able to efficiently exploit the parallelism. Assembling, programming, and ensuring correct operation of computing systems that will involve hundreds or thousands of processors, or cores as they are called now, will become a major challenge as the complexity grows exponentially with the number of these cores. Until fairly recently, these three domains were entirely isolated, and each of them had its own design methods, market segments, and dominating industrial players. What is needed is a unified approach to computer system design applicable to these domains to achieve interconnectivity at all levels.
Understanding and solving the problems in parallel computers was not easy. Solving real issues in this field required highly skilled people from different disciplines to work together, no matter if they were scientists, developers or manufacturers, and this from all European countries. This is why Sarc is a real European project.
But how to explain all of this to a non-scientific audience? Let's try an analogy. Barcelona, city with a history, city of expansionism. Consider the quality of life of her citizens as the software in computer systems. The buildings, infrastructure and facilities such as shopping centres, sporting accommodations, and industrial areas being the hardware. Decisions made by the municipality, set in construction specifications and tenders to constructors of urban sprawl, could be compared with computer architecture. No doubt that building or expanding a district is something completely different from developing an entire new city for the future. An old city or village cannot form a solid base for residents that can fulfill all future demands. Construction specs should meet future building capacities one cannot foresee nowadays. Yet an unexpected explosive growth of population must still leave the possibility to double the size and infrastructure of a city without interrupting its daily life. Otherwise, its population could feel the urge to move somewhere else. Back to computers. Building tomorrow's computers of any kind will also require a harmonious interactive approach between hardware and software orchestrated by the computer architecture in order to enable smooth future expansions. The Sarc Project laid down the strong fundamentals for real solutions of the wide variety of problems parallel computers have to cope with. The Encore project, a direct Sarc successor, is just one of the proofs that Sarc was quite successful in reaching its goals.